This video will cover the reaction of alcohols with HCl. Reactions of alcohols with HCl are a lot like the reactions with HBr, except that remember that chloride is a weaker nucleophile than bromide. Remember that chloride is smaller and more electronegative than bromide, making it a weaker nucleophile. The treatment of an alcohol with HCl will produce the alkyl chloride. And just like with HBr, the mechanism will depend on the structure of the alcohol. Tertiary alcohols will typically undergo an SN1 reaction. Consider this tertiary alcohol. It will react with HCl in an SN1 mechanism to give the alkyl chloride. The mechanism looks like the mechanism with HBr, with the first step being protonation of the alcohol to improve the leaving group. In the next step, water leaves to produce the carbocation. Then, chloride ion that was produced in the previous step attacks the carbocation to give the alkyl chloride. Remember that the SN1 mechanism results in racemization if there is any stereochemical information in the starting alcohol. When considering the reaction of a secondary alcohol with HCl, we have to remember that the SN1 mechanism is always slower in a secondary substrate than it is in a tertiary, because the step leading the rate determining step. When considering the reaction of the secondary alcohol with HCl, we have to remember that in general, secondary substrates react more slowly in the SN1 mechanism than do tertiary ones, because the rate determining step, which is formation of the carbocation, is slower when that carbocation is secondary. Combined with the fact that chloride is a weaker nucleophile, secondary alcohols typically react with HCl incredibly slowly, too slowly to be useful synthetically. Therefore, a catalyst is typically used with secondary alcohols. The catalyst that is used is called the Lukas reagent. Lukas reagent is a mixture of hydrochloric acid and zinc chloride. Zinc chloride is a very strong Lewis acid that helps to speed up the reaction of secondary alcohols with HCl. Let's consider the reaction of this secondary alcohol with HCl and the Lukas reagent. In the first step of this mechanism, the alcohol attacks the Lewis acid, the zinc, to form a better electrophile. Next, the leaving group leaves to form the carbocation. This step occurs much more quickly with the help of the strong Lewis acid, zinc chloride. In the final step, chloride ion attacks the carbocation to produce the alkyl chloride product. Because secondary alcohols treated with a Lukas reagent undergo an SN1 reaction, the product racemizes if there is any stereochemical information in the alcohol starting material. Finally, let's consider the treatment of primary alcohols with the Lukas reagent. The reaction of a primary alcohol with hydrochloric acid would result in a very, very slow reaction because chloride is a worse nucleophile than the bromide, slowing down the rate of the SN2 reaction. We can speed up the SN2 reaction again by using the Lukas reagent. Let's consider the reaction of this primary alcohol with the Lukas reagent. Just like we saw with the secondary alcohols, the first step is attack of the alcohol on the Lewis acid. This produces a good electrophile that can react with the chloride ion. The chloride ion attacks, kicking off the leaving group in an SN2 mechanism to produce the alkyl chloride product. If the starting alcohol has chirality, we will see inversion of stereochemistry in this SN2 mechanism. Because the SN2 mechanism involves a rate-determining step with two molecules, this occurs much more slowly than the SN1 reactions of secondary and tertiary alcohols. Because of the differences in reaction rates, we can use the Lukas test to distinguish between primary, secondary, and tertiary alcohols. This test is performed by dissolving the alcohol in a solution of zinc chloride and hydrochloric acid. This produces the alkyl chloride product. The very polar alcohol is soluble in the zinc chloride and hydrochloric acid solution. The product alkyl chloride, however, is insoluble. Once the product is formed, it forms a second phase, and we can observe the second layer as evidence that the reaction has occurred. Then we measure the rate at which this occurs. We know that primary alcohols react very slowly, even with the Lukas reagent. Typically, primary alcohols take more than 6 minutes to form the second phase. Secondary alcohols react intermediately. Typically, it takes between 1 and 5 minutes for a secondary alcohol to react with the Lukas reagent and form the insoluble second phase. Tertiary alcohols react most quickly. Typically, the second phase is observed in less than a minute. Using the formation of the second phase and the rate at which this reaction occurs, we can distinguish an unknown alcohol based on whether it is primary, secondary, or tertiary.